Okay, so hi everyone, welcome back to the channel, and today I'll be attempting CodeChef Lunchtime. So it's about to get started in another 20 seconds, and I'll be participating in Div1. So let's see how it goes. Okay, so there are two submissions already on this problem. So I guess the problems got opened for some people and they were able to submit them. Maybe that is why. And also they've skipped around 5 minutes of the contest already. So yeah, let's see. You're given a sequence A1, A2 up to AN. You may perform the following operations any number of times. Select any two adjacent elements AI and AI plus 1 and replace them with this. Okay, a real number without rounding. Okay. You may also select each pair of adjacent elements and each element to replace in multiple operations any number of times. Okay, I did not quite get this one. You may also select each pair of adjacent elements you may also select each pair of adjacent elements and each element to replace one of them. Okay, that is fine. Any number of times. Okay, is it possible to make the sequence strictly increasing in a finite number of operations? So if we have 7 and 4, clearly after any sequence A1 is greater than A2. Okay, so if we have 1 2 2, so we can change A2 to 1 plus 2 by 2. The sequence after this operation becomes 1 1.5 and 2. Right, so this is strictly increasing. Yeah, that is fine. Okay. So strictly increasing. If we have 7 and 2, so what can we do? We can make okay, so we want the last element to be as large as possible, right? And we want the first element to be as small as possible. Both of them actually mean the same thing. So like can I do something that transfers some amount of numbers from here to the last one and do it like many times? So now when will it be useful to do the operation here and replace 9 with it? Only when, if let's say 11 was here, then 11 plus 9 by 2 will give us 10, and that will definitely increase 9 by 1, so that is a good swap. But then so like if we have 7 and 2, so we can obviously increase it. Yeah, that is fine. And n can be up to 10 to the power 5. Okay, so if I increase 2 by, so 2 can become 7 plus 5, 7 plus 2 by 2. Then I can again increase 4. Now obviously, like, increasing one side is symmetric to decreasing the other side, so that should not be an issue. Okay, so yeah, So if I have some numbers and I keep increasing them, then this is one way to increase them, right? So that is fine. This will increase only when this number is greater than or equal to this, right? So let's say we've increased this one, and then similarly we can increase all the numbers, and then what you can do is then we can start decreasing from that end. But that's like pure greedy, and I'm not sure if this can be proved. I think just one pass should suffice here. Like, this is an intuition that I'm getting. So if I just make one pass and if the array is increasing, then it's fine. Otherwise, what can we say? Like, we tried to increase every number, right? And now we cannot increase any number here by doing such a swap, right? Like this and this. But we can obviously, okay, so like if it is A and if this is B, and if B is greater than A, then it is fine. If A is greater than or equal to B, then I can replace A by A plus B by 2. But that will not help, right? That won't help because obviously this one will still be greater than B. Or can it be less than B? Yeah, we are not sure here. So A plus B is greater than less than 2B. So A is less than B, but that is like a contradiction, so that cannot happen. So I think one pass should suffice here. So yeah, I'm going to do a single pass and this should work. Because if it does not, then there will be some pair such that A is greater than B, greater than or equal to B, right? And let's say till here all the elements were less than A. Then let's say this was X, then we can have this. Then obviously we'll have to replace A, right, with something. Okay, A is greater than or equal to B. But if A is greater than or equal to B, then I can definitely replace B by A plus B by 2. And this will definitely increase B for sure. So like I'll have B plus A by 2 and I'll have A. Okay. Okay, so if we had 7 here, then we could have done 7 plus 2 by 2, and we could have decreased 7 here at this point. Yeah, we can decrease 7, that is fine. But if we wanted to increase, then the second number can never increase, right? So if we have 7 and 2, seven plus 2 by 2, and this becomes what? This becomes 9 by 2, that is 4.5. Then I say 4.5 plus 2 by 2, and then this becomes like something like 3 point something, and at the end we'll have something like 2 and 2 by 2, 2 plus 2 by 2. Right. So if you have 7, how about to increase this one? That does not help in any way. Yeah, 1 and 2. Then we can do, yeah, so that number becomes less, that is fine. Now what I can do is, if I have x and y and x is greater than equal to y, right? So what I can do is, I can completely reduce x to y by simply halving, right? So what happens is that we'll get y and then we'll also have y, but they both are equal. So I need something here to increase this, right? If you have x and y and y is already greater than x, then there is no problem. But if you have x, okay, let's consider a triplet here because that is important. So let's say you have x, y and z, and x is greater than y, but y is greater than equal to z. So then what happens is, then you can reduce y to something like x point 001, okay, 0.00001. You can reduce it to something of this form. Now if x is less than z, right here, if x is less than z, then we can say that this is fine and we can skip this y in that case. Yeah, right. So what we want is x should be less than z. Right here. So this number can be reduced to something like 2.0001, and then, or you can say it becomes 2 only completely. Then you just need to increase this 2. How you do that? You will take help from the next one. Okay, seems like very tricky to me. So yeah, for n equals to 2 this is simply not possible. Then a plus b by 2. Okay. Okay. So like if we have three elements x, y and z and x is less than z, then we don't really care about y in that case, because y can be brought to a certain point that it lies between x and z. So that is fine. Then okay. If we consider only three elements, then so I'm not really sure about how to do this one. Okay, so if the whole array is completely decreasing, then we simply cannot do anything. But let's say there is some peak at a point, then what can I do? Then using this peak, I can align all the elements here. And I can do this. Then okay, so now the thing is that if the whole array is completely decreasing, or let's say less than or equal to something like that, then we simply cannot do anything. If the whole array is something like this, then we cannot do anything. But let's say this is decreasing, and let's say I get a peak somewhere that, not a peak exactly, but something that's not completely decreasing. Then what I can do is I can choose this element and I can bring all of these elements to somewhere here. Right now, this element is, let's say, yeah, I'll bring it such that if this is A and this is the last Z, then Z becomes greater than A. Then what I know is, then I know that this is of this form, right? Then what I can do is, okay, so if I decrease this to this point, then this will still be decreasing, right here. But what if I decrease this one first of all, and I bring it here? Then this element, if it is not at this point, okay, this is still confusing. So if I have just one peak somewhere, then I can bring all of these elements to this, and they all will be greater than this one, but they all are less than this. So what I do next is I bring it here such that this remains increasing, but then this element is here, and then this is a peak. So that will work as well. So I'm assuming that this becomes like this at some point. Then what I can do is, so then I have these points, right? So I can simply reduce them all to this form, all increasing. I think this should work, but yeah, I'm not sure. So as long as there is one such pair such that a is less than b, this should work. Why is that so? Because all of these elements that are here, right, let them be greater or less than a. What happens is that, you know, if they're less than a, then it does not matter. If they're, let's say, greater than a, then I can reduce them to something of the form a.00001, and after they all are of this form, let's say this is whole increase, whole, what can you say, let's say this is whole decreasing also. Then what you can do is, then you can put a to something like b minus 0.00001, so it becomes very close to b, and then you have this whole sub problem again, right? So this is solvable. And what about the other side? So if b is greater than, even if you have all these elements less, then you can put them to something like b minus 0.00001, and then you can reduce b, and then it becomes like a simple subproblem again. So this is solvable, yeah, as long as there is one pair such that the right one is greater than the left one, then it's possible. Okay, let me just check what is the range of n. Okay, so I think they should work on the sample ones. Fine. Fine, that is great. And the great part is that I first proved this and then I did the greedy part. I mean, it was not greedy, it was obviously an intuition. So the great part about this question was that I actually proved this and then I actually started coding it. This is not something that I do in every contest. I mostly rely on my intuition, but yeah, it felt really great. So yeah, moving on to problem B. Now already a lot of time has been wasted in the first problem, but yeah, I'm happy I was able to do it, and I was able to do it after proving it. So yeah. Okay, so magical sequence. The group of high magicians said wants to buy the sequence from him. They calculated its cost as follows. Choose a sub-array of length at least 2, a contiguous subsequence. The cost is the difference between the largest and the second largest element in the sub-array. Oh, okay, great. Note that there is more than one element with the maximum value. The cost is 0. Yeah, that is fine. Clearly the cost is not uniquely determined, but depends on the choice of the sub-array in the first step. So what they want is choose a sub-array. The cost is the difference between the largest and the second largest element in this sub-array. So note that if there is more than one element with the maximum value, the cost is 0. Fine. Clearly the cost is not uniquely determined. So he wants to find the number of different possible amounts of money he can obtain. The size of the set of all possible costs for all valid choices of his sub-array. Great. Denoting the number of test cases. Okay, fine. All of this is fine. Obviously this one can be done in order of n square. But yeah, we'll have to think of something like order of n log n or order of n. The different costs, right? Just a minute. What else are they saying? Contiguous subsequence. Okay, fine. So here we can have 4 and 2 basically. So yeah, we need to find the number of different values that we can obtain here. Okay. So ten to the power 6. Fine. Okay. So if I consider any subarray, then I'll have the maximum and I'll have the minimum. I mean the second maximum. So let's say the maximum is this and the second maximum is this. Then what we do is then we can extend this to a point. Like if this is the second maximum, let's say this was x, so I can extend it to a point such that so for if you want x and y, let's say, and if x is less than equal to y, then what you want is we cannot pick any number from this side, but this does not help in any way. So the order of n square solution is pretty clear to me, and it should also work. So for the time being, I'll just quickly do that. guess doing the brute force one will, help me in thinking about the actual one, because then I can try out some possibilities here, like to maybe like get an upper bound of the answer. Okay, so okay, that is insane actually. Okay, so that solution went through and that is fine. I was expecting 30 points on this one, so yeah, that is fine. So yeah. I just want to check like what is the answer that it is throwing. One, two, three, 7, 7. And that is like just a random thing that I'm doing. I'm just checking like what are the answers that I'm getting. So yeah, these seem to be pretty close actually. Like I'm not sure how come the answer is so close. But I will see this. So yeah, like that is the brute force way of doing this, and we'll have to think of something clever here. So let's say I consider only the maximum values. Okay, so let's say this is my maximum. Then I know that if I'm standing here, then I can extend this segment to a point till till I don't get a greater value, right? Till all the values are less than or equal to, and similarly here as well, till all the values are less than or equal to this max, I can extend my segment here. Now for this point, what I need to do is okay, so how about I consider it like this, that if I have the whole array, then there will be some maximum and then there will be some second maximum, right? S max. Now the thing is that if I consider this whole array, then let's say this is the second maximum position and this is the maximum position. Then as long as I pick an ending index from here and a starting index from here, all of their answers will be same, which will be this max minus S max. Or a better way to look at it would be, okay, yeah. How about I do it like this, that if I have a max here, then I find the second maximum which can come along with this. So if I have a max at some position, I'm required to find a second maximum. So what are the different values of second maximum that can come with this? That is the point. So let's say we have A and we have B and we have C. When is it possible to go from A to C? This is possible only when you go from A to C, there is no bigger element here than C, obviously. So like if the next greater element for C is A, like the next or the previous, then this can count, right? Yeah. And if this is A and let's say this is somewhere B, okay, so this problem is like actually getting reduced to finding the next greater element, right? Yeah. So if I have A, B and C with A greater than equal to B greater than equal to C, and if I'm at C, then I can go in this direction to find a greater element or in this direction to find a greater element. Now the first greater element that I come across, that will get added to my answer, right? Yeah. like that will get added to the set obviously. So but this shows that we won't have greater than n values, but this is like 2 into n. Yeah, we won't have greater than 2 into n values, I guess. And what are we doing here? I'm pretty sure that the values that you were getting, they were for this, no? Yeah, so like the bound is basically like 2n. So I'm kind of getting a hang, I'm able to understand it now. So the thing is that if I'm at C, and let's say C is my second maximum, then I can go in this direction to find a maximum greater than C obviously, and or I can go here, right? So as soon as I find a greater element, then any other segment that I consider, you know, will not either have this as the second maximum or yeah, like we're not really concerned about the number of segments that it comes in. We are simply concerned about whether we are able to get an answer of this form, right? So I think this should work, and the bound will be then 2n because I'll be considering in both the directions. Yeah, this seems pretty cool. Because if you consider any further segment than here, like they can have the same second maximum and maximum, but as soon as you get a value that is either here or let's say here, I mean if this is A and if this is C, then if you get a value in between them, then your second maximum is getting spoiled, because then you cannot have C as the second maximum. Similarly, if you get a value that is greater than A here, then you know that the second maximum won't be C, right? So yeah, the bound is basically like 2n here. So this should work actually, and I can do this in order of n with a stack. But I'll still have to maintain that unordered set, I guess. But still, like 2n is actually really great here. So I can have a stack here. Okay, so we want the next greater, right? So yeah, that will go from left to right. So what we can do is we can insert here push 0. So we need the next greater, right? Greater than or equal to, basically. Yeah, right. Greater than or equal to, right. So okay, so next one, right? Push out. Yeah, this should be fine. def greater dot push, and I can push n-1 here. Okay, so are these values okay? That is fine then. And I can simply test it with random inputs as well. Okay, this should be this only. Yeah, this is fine. Okay, so let's test it. Gives the right output here, but I'll have to check it. Okay, gives the right answer on random inputs as well. And I'll check it for some more. So maybe I'll check it for 5. Okay, I'll have to return this one. Okay, seems to be giving the right answer on every input, so I'll have to submit it now. And I'll quickly comment out this part. Okay, well, this was not what was intended here. Not sure. Okay, fine. If I get a TLE, I think I'll have to switch to the ordered set instead of the unordered set. I mean, not the ordered set, but the simple set. Okay, let's see the other problem still then. Okay, great. It worked. So partition the vertices of G into two sets A and B such that each vertex of G belongs to exactly one of these sets. A is non-empty, A is independent set in G. Okay, fine. For each vertex A as an element of A, each vertex B, there is an edge AB. So like something like a bipartite graph, but it is not necessary that both of them are. I guess it is necessary. Yeah, but like A is one of the partite sets that is independent, but B is not necessarily independent. Number of such partitions. Or determine that no such partition exists. Fine. A should be connected to all the vertices in B. That is another major constraint here. Okay. Moves to cell AI. Chefs move at the same time. Okay. This seems really tough to understand. I think I'll have to stick to the third problem. A is non-empty, that is important. A is an independent set, okay, that is fine as well. Okay, how about I try this sub task first of all. So, okay. I think the very first thing to notice here is that if you have so many nodes here, then let's say I put this as A, then what happens is that every node, every vertex that it is connected to, it uh, it actually becomes in the set B, right? And then what happens is that any other vertex that has not yet been into the set B right now, then that cannot be in set B. This is because A won't have an edge to that node, so that definitely cannot be in B, but it can be in A, right? And if it has to be in A, then it has to be connected to all these B nodes, right? Yeah. So it is basically like finding out the different sets that you can get, different sets of A basically. So what happens is that as soon as you fix one node in the set A, then all the nodes in the set B get fixed, and all the nodes in the set A get fixed as well, right? So now what we need to check is that if that is a valid configuration or not, right? So yeah, I can maybe store all the vectors, then comparing them at the end again would be like order of n square, but yeah, since we're only concerned about order of n square here, I mean order of n into m, then this should be fine, I guess. Yeah. Yeah, I'll think about the bigger subtask later. I think I should code up the smaller one because I'm not sure if I'll be able to actually think about the bigger one till the very last. So I'll just simply code it. Okay. And we have to print one of the configurations. Okay, so I can basically store them in a string and then comparing them would be easier. Fine. So okay, I should just name it boss. Yeah, that is fine. And what do they want us to print here? Okay, I've opened the wrong one. So another intuition that I'm getting for the larger subtask is that there can be at max two configurations, at max two such configurations, but I'll have to check it. Undirected, then each vertex of Fine. If there is a vertex that is in the set A in one partition, and fine. Find the number of such partitions. Great. So, A has to be non-empty, but B can be empty. That is another thing. I can simply check it here only. There are no self loops or duplicate edges in the graph. Fine. Oh, okay. I can consider it as one only. So for B, we don't need to check anything, only for so that will become an order of n cube solution then. But will order of n cube work here? That is the point. It won't. So what else can I do? I can basically no, that won't work. So what I need to check is if they both are connected or not. So maybe I can maintain a matrix. Let's have it as a vector only. but I could have done that simply by comparing all the edges. Yeah, okay. Why did I do this? A.insert hi. If this should be n plus m, right? Yeah. Seems to be working fine. I'll just try out some simple cases. Okay, so if I take 1, then 2 has to be that. So they should not work, they should give 0 as the answer. Okay, it actually gives 3. So like, so if I take the third element to be in set, oh I see. If I take the third element to be in set 1, that is A, then it has an edge from 3 to 2 and 3 to 1, right? Yeah, oh, that is great. So this is working fine actually. So I'll quickly submit it and then maybe think about the bigger test case. So obviously there are not more than n such possibilities, because as soon as you fix a vertex, the other ones get fixed automatically. So it boils down to basically checking out every possibility, but there has to be some clever way of skipping that. Partially correct. Okay, that is great actually. Okay, so how about I try out the first possibility and see if it works or not. That means just put 1 in the set A and then check. So if it does not work, then this has to be definitely in set B, right? Yeah. So as soon as you put it in set B, then you have a choice. Like the major task is to determine which element to put in set A, basically. Fixing one of the A's actually fixes the whole thing. But fixing a B does not fix the configuration, definitely. The task is basically to check if A can be put into set A or not. I mean if X can be put into set A or not. That is the major task at hand. And there is an hour to go still. So far so good.